Hello, this is Brian Washburn. I'd like to talk about writing expressions for velocity and acceleration in spherical coordinate systems. We already talked about cylindrical and Cartesian system. Some problems we're going to deal with geometries where the problem is a lot easier to be solved in a spherical coordinate system, so I like to be able to write down V and A in the coordinate system. So what I have shown here is I have a Cartesian coordinate system. It's always good to go back to a Cartesian coordinate system. I have some point in space in this, and I have a position vector R. What I like to do is first start and write down the position vector in spherical coordinate systems. Obviously, a point in a spherical coordinate system has a R value, a theta value, and a phi value. In general, for points, R is basically so R is a distance from the origin to the point in space. Phi is an angle with respect to the z-axis, and then theta is, and then phi is called the azimuthal angle, and that is in an xy plane. What I'm showing you here. A position vector is quite simple in a Cartesian. In a spherical coordinate system. A position vector is this going to be equal to R, that's my position vector, is R hat. Okay, and what is R hat? R hat is a unit vector, again associated with each instead of having x, y, z, we have R, theta, and phi, and thus my position vectors are, I'm going to have R hat, theta hat, and phi hat. And so let's write down what these directions will look like. R hat is along the R direction, so it's going to be a unit vector that points like this. However, notice that R hat will depend both on theta and phi, and that's what makes life very complicated. So again, R hat points in the direction of increasing distance from the origin R. Okay. What about theta hat? Theta hat points in the direction of increasing theta. So, theta is measured with respect to the z-axis. So again, increasing angles go from here to here, and so I would expect that direction of increasing angle theta, and it gets hard to draw here, but it's going to point like this. It's a unit vector that's going to point like this. Okay. Now, what about phi hat? Phi hat points, again, phi is measured with respect to the x-axis. It points in the direction of increasing phi. So it's actually going to kind of be in the page. I'm going to draw it down here. Phi hat is going to point kind of like this here. Unit vector points. And so I'm going to get a system, again, all those vectors, even though it's hard to see in this two-dimensional drawing, are perpendicular to each other. So R hat dot theta hat is going to equal to 0. R dot phi hat is equal to 0. Okay, so those are my position vectors. And now what I want to do is I want to write down velocity in terms of those guys. Now before I do that, it's always good to write down the position vectors in terms of Cartesian coordinate systems. Okay, and that's where you need a little geometry and life gets a little complicated. But let's take a look at R hat. R hat is a line like this. Okay, if I make a projection of that into the xy plane, what I'm going to see that's what this dotted line here is. And so notice that makes I have a cosine direction here and a sine direction here. Now, if I look at this component here, I can draw a little triangle here, and use a black line for that. So notice what I can do is I can make a parallel line like this. Okay, now notice I have a right triangle. I have a right triangle here. This component here is going to be the sine component of R. Okay, so this is really R sine theta. Okay, and then that's this length here, and then I take that guy here, which is the same thing, in the xy plane. So that now allows me to write down a position vector for R hat in terms of my Cartesian coordinate systems. Okay, and so what I would say is So let's write down r hat. R hat is going to be equal to, now again, what I have is I have this sine theta component broken up into components in the xy plane. So I'm going to have here is sine theta, and then the component of that along the x direction is cosine phi x hat. And again, the sine theta component is this guy here, but along this axis, that's cosine of phi. All right. Then you would expect that, okay, in the y component, I'm going to get, again, it's sine theta, but now I'm going to have sine phi y hat. And then in the x or z direction, it's just going to be cosine theta, which is just this component right there. Okay. That's r hat. Okay, now you can see this gets really confusing really fast. Let's write down theta. Now theta hat is going to be a vector that's going to be perpendicular to that. And again, using similar geometrical arguments, instead of saying sine, we're going to write cosine theta. And then we're going to put cosine phi. Sorry, not phi hat. X hat. Okay. Plus cosine phi sine. Cosine theta sine phi y hat. And then we're going to have minus sine z hat. And the reason why is because the minus sign, because this guy, the angle's positive angle goes in this direction here, so it kind of points down. That's where the minus part comes in. Okay, and then the final guy is theta hat, or phi hat, sorry. Again, that guy here, that's this guy here. And notice that's just in the xy plane. So, and it looks just like phi hat in a cylindrical coordinate system. Cosine. And there's no z component. All right. So why do we have to know all this? Well, we're not even to velocity or acceleration just yet. So how are we going to get velocity? Okay. Well, velocity v in a spherical coordinate system is just that, or really the rate of change of the position vector there. Now we can use the chain rule to do that, and we're going to get here r hat, and that's going to give me r hat plus r hat dot. Okay. Now this term here is pretty straightforward. What's not straightforward is r hat dot. You have to take the chain rule of all this stuff here, and notice that theta and phi both depend on time. X hat, y hat, and z hat, they're constant, so they don't. So you have to take a chain rule of all that stuff right there. Yeah, good luck. And so you can do that. And what you can show just by doing that, and so is, again, you have to take the chain rule of this. So that, for example, let's work through this a little bit, this first term. So I'm going to get, say I take the derivative of this, I'm going to get, well, let's just do it on, so say I look at just that first term there. So I'm going to say ddt of, and I just want to do a couple terms to show you how nasty this gets. So say I just want to look at just that term right there. Okay, well, that is going to be equal to sine theta dot cosine phi x hat plus did I do that? No, obviously I did that wrong. Sorry. Already I'm making mistakes. They ain't good. So we're going to have cosine phi dot. Okay, and then we're going to have here a minus sine theta sine phi dot x hat. Okay, and that's just this first term. You got to do this term and this term Yeah, it gets really nasty really fast. So you can, if you get really bored in life, you could do that. I'm just going to write down, but I'm going to write down the solution to that. So what we're going to do is we can express that derivative in terms of the other hat. So I can show that r hat dot is going to be equal to, let's see, just looking at this real quick. Okay, so writing r hat dot is going to be equal to, what do we have here? We have v dot v hat plus r sine theta, so theta dot theta hat plus r sine theta v dot v hat. Okay, now if you take this guy and you put it back into this equation here, you can show that v is going to be equal to r hat, r dot r hat, r theta dot theta hat plus r sine theta v dot v hat. Okay, so that's cool. So that is the velocity in a spherical coordinate system. And we'll be using that result in the class. Okay. So what about acceleration? Acceleration. So let's go to the next page here. So now what I want to do is write down, sorry, let's do that again. Okay. Okay, let's move that down here. That didn't work. Okay, so now this is my expression for velocity in a spherical coordinate system. Now what we're going to do is acceleration. All right. So acceleration, again, going back to what I have here, acceleration is equal to v dot or r double dot. Okay. So now what you have to do is you have to use a chain rule for all these terms here. And that, again, gets very complicated. What I'm going to do is I'm just going to write down the solution since this is just an introduction. So we can say that A is going to be equal, again, I'm going to get r hat, theta hat, and phi hat terms. And writing it all out. So I'm going to get, oops, sorry, that's not a vector. So I'm going to say that the r hat component is going to be r double dot, okay, minus r v hat sine squared theta minus r d double dot squared. That is the r hat term plus r theta double dot plus 2 r dot theta dot minus r phi dot squared sine theta cosine theta, and that is the theta hat term. And then finally we have the phi hat term, r phi double dot plus 2 r dot phi dot sine theta plus 2 r theta dot phi dot cosine theta, and that is the phi hat. So that is the acceleration in spherical coordinate systems. Oh boy. Now this we'll be using this and it'll be given to you if you ever need it. It's hard to drive. It takes a lot of terms. Basically, you have to take the chain rule of these terms and then pull out these r hat and phi hat and theta hat terms and rewrite it into this expression I have right here. Okay. One way we can check, say, well, how do we even know this is even correct? Notice that acceleration has units of distance per second squared. Obviously, this is distance per second squared, but notice that here r has units of meters. Phi dot has units of seconds, but 1 over by squared, so that's 1 over second squared. Same thing with r times theta dot. R has units of meters. Theta dot has units of 1 over second and 1 over second squared. And then you can look at terms like this. Like, for example, look at this term here. I have 2 times, meters. R is meters. 1 over second, 1 over second. It gives me units of meters per second squared. So it has the right units. Okay. So there you go. So what we did was we went ahead and derived expressions for velocity and acceleration in spherical coordinate system. Okay. Now, you got to remember, when we're going to use these things, life may be simplified. Okay. And let me give you an example. Say I have a problem where I have a bowl. Okay, and a bowl can be thought as a hemisphere like this, and say I have a marble on the bowl. And so where would I put my coordinate system? I'll put my coordinate system here. And so think about this, that the distance from here to here for the center of the mass, from the center of my coordinate system to the marble, that doesn't change. Okay, so we would call that equation a constraint. That means that r, which is the distance what r is the distance from the center to where the object is, r is a constant for all times. Okay, so that's nice, and we can say it's the radius of the sphere of the bowl. Okay, well, that means that eventually when we solve a problem like this, r dot is equal to 0 and r double dot is equal to 0. That simplifies these equations quite a bit. Okay, because then you can see that, all right, well, this term here is 0, that term is 0, that term is 0. Okay, and so then the object can only move. So in this case, the object is basically 2-dimensional. There's the dimensions. The 2 free parameters are basically theta and phi. Okay, so that simplifies both the velocity. Well, it definitely satisfies the velocity, because then this term is 0, and then we will have these terms here. And acceleration simplifies a little bit as well. Okay, this is Brian Washburn. We'll talk to you later. Goodbye.